So I think we will start now. I will share my screen. So are you able to see my screen?
Yes.
Okay. So what we are going to do today is like in last class we learned about the principles of remote sensing, but it was like we were not able to cover the question answers properly. So we will try to solve that thing first, and if time permits, we will see other concepts. So like till this week, like entire content of remote sensing is going to be over, and from next week onwards, you have lectures on GPS. So what we will do also, like if some like remaining numericals are there on the concept on remote sensing only, that we are also going to cover today as well. So first of all, we will see some questions based on the week this week's content. So first question is like higher DN values represents which color? So can anyone tell this answer of this one?
The brighter color.
Okay. So why brighter? Because like if higher the DN value is nothing but the digital number. So the energy which we are getting back from like after the reflectance value which we are getting back at the satellite. It means if the reflected energy is high, then it will show the more brighter color. And if it is less, then it will show the darker color. And in between, it will show the shades of gray. Now the next question is like when we are using the remote sensing, then if we are using sun as a source of electromagnetic spectrum, then that remote sensing is known as which kind of remote sensing?
It's a passive remote.
Active.
Exactly. Exactly. And what about active?
So when it's direct, not influenced by any outside source of energy.
Exactly. So basically in active we have our own source of energy, and other two options like GIS and GPS. So these are the part of advanced geomatics engineering. There's also nothing to do with that. Then after 16-day temporal resolution, so there are the different series of Landsat satellite. So you can some of the questions are like now it's remembering based questions that you have to keep in mind what is the temporal resolution, radiometric resolution, spatial resolution of various popular satellites. So like which of this one is not having 16 days temporal resolution? All of it like Landsat only.
Sir, I think the latest version lands at 8 won't be in this list.
No, the answer is so latest one is having 16 days. But apart from that, 5 and 7 also have 16-day temporal resolution, and the earlier one it is not having 16 days. So oldest satellite is not having 16 days; it is having 32 days, I guess. Okay. So now the next one is like which is not a polar satellite.
Sir, INSAT.
Inset satellite. So that is not a polar satellite. Other three are the polar satellites. Now the next question is resolution of panchromatic band of sport 6 data is. So first of all, I will tell you like what do you mean by panchromatic band. So panchromatic band is means just like instead of a particular wavelength, it uses the larger chunk of the electromagnetic portion, and because of that, we are able to get more amount of energy at the satellite, and because of that, we can increase this partial resolution. And now using this particular band, we can do the pan sharpening operation, which means if we have data sets of let's say 30-meter resolution and panchromatic band if we have 15-meter, then we can convert that 30-meter data to 15-meter data using the panchromatic images. So that's why these images are useful, and main idea is they are having a big window of wavelength. Because of that, energy which we are receiving, it's very high. So here you just have to recall like what is a panchromatic, like resolution of panchromatic sport 6 data sets.
Sir, 1.5 meters.
Yes.
And
So now we have this Indian remote sensing satellites, IRAs, P6, the application of which, like main application of it or uses for which applications?
Agricultural.
Yes, so it is used for agriculture applications. Then satellite providing the image of less than 5 meters spatial resolution. So in that, like if you will recall that Econos, QuickBird and Worldview satellites are there. They are
Yes.
having less than 5 meter. Otherwise, now you have to arrange the according to the lower resolution to higher resolution. So you just have to remember the spatial resolution of each and every satellite, and based on that, we just have to put in arrange in order. So can you recall it?
So I can just recall the quick word on the restart.
Yeah. So this no need to. I mean, this kind of question is just for remembering purpose only. Like when you are dealing with a data set, you have to decide like which data to use. So do not worry about this exact remembering. So this is just for this examination purpose only. Otherwise, when you are dealing with the actual real life applications, we will construct a matrix of spatial resolution and temporal resolution, and based on that, we will search the data sets and we will use the product. So no need to worry about that. And most ofly, all the satellites which are shown here, like which are giving a very high resolution, all of it are like a paid one, commercial one. So if we want to get that imagery, we have to pay for it. So basically, what you should like remember for a research purpose, like which are the popularly satellites which are available free of cost. So in that case, Sentinel series is there, Landsat series is there, Modi series is there. So you should remember all those kind of resource that is there. So temporal and spatial resolution of those satellite rather than this one. So this is just for like bookish knowledge. So then after we have the correct statement in case of microwave remote sensing. So which one of it like it's true? So we'll start with the first one, whether the first one is right or wrong. But like microwave region falls between the infrared and the radio emission.
Wrong, sir.
Uh, it's a right one. Then the second one is like micro region extend from point 0.1 to 0.5 meter. That is wrong. So it's 1 to 100 meter. So the first one is correct. It falls between the infrared and radio waves, if you recall it. Radio is like higher than the microwave, and the infrared is lesser than the microwave. And then micro remote sensing, when we are using, it is using their own source of energy, and that's why during clouds is there or rainfall is there or cyclone is there, we can penetrate through the atmosphere or rain and we can collect the data set. So the last one is right. And then we are using our own source of energy, and because of that reason the third statement is not correct, because it is having active sensor. Then the next question is Hyperion datasets. So Hyperion is a like hyperspectral satellite image. So, hyperspectral, it means like it has more number of bands. Like when we talk about RGB band, it's just zero point 0.4 to 5.5, 0.5 to zero point 0.6, or zero point 0.6 to zero point 0.7, like that only. But in case of hyperspectral remote sensing, we have more number of bands so that we can get the minute detail of the object as well. So which of the following is like right? So we can see like from the definition only, the last statement is right because it has more than 100 spectral bands. Apart from that,
So I think first
the
statement is also right.
yes, exactly, because using this normal bands, we cannot find out the minerals composition which are there. We need a very high spectral resolution because each mineral will behave differently in a different wavelength. So if we take just two rocks also, it will look similarly if we take RGB or infrared image. But if we penetrate the different amount of wavelength, it can be changed, and like we can find out the difference between two different rocks as well. And then the second statement is wrong because it has 16-bit resolution, and then swath is also not 1 kilometer. So this is just an example of like last year's question assignment of the same content. Now what we are going to cover is we'll cover the whatever the remaining questions are there from GATE syllabus. on this remote sensing chapters. We will going to cover that one. So now when we just recall the spectral signature. So spectral signature of an object in a satellite image does not depend on. So what might be the answer according to you?
Square width of satellite.
Exactly. But now we will decode the answer as well. So if we take the season of year, so in that what will happen that if we take a image during the if we take the remote sensing of vegetation, so during the crop growing season it has very green color, and then once the crop is like about to just harvest, it will become like different colors like golden brown if we take the rice as an example. So the chlorophyll content will go down, and because of that its signature will change in the same wavelength. Earlier it was reflecting green, but now it is reflecting some other color. So it depends on the season of the year. Then we take the wavelength of electromagnetic spectrum. So it's like a main definition of spectral signature is on build up on this wavelength concept. Like what is the response in the different wavelength of what is the response of the object under the different wavelength of electromagnetic spectrum. So that's why that is also correct one. Then the third one is like swath width. So how much area the satellite is covering. So it doesn't depend on that, because if satellite is covering 5 kilometer area or 10 kilometer area, it will not affect on the property of the object. So that's why this correct answer, like it does not depend on the swath width. And the last one is the reflectance value from the object. So it's also like primary property. We'll plot the y on y-axis reflectance and x-axis wavelength. So it depends on B and D and also. So the right answer is C. Now the next one is thermal infrared images are provided by which satellite? So do you know this thing? So thermal infrared, it means it falls under which part of electromagnetic spectrum? 3 to 10 micrometer. And if we see that Landsat satellite is having one band into it, if you recall that in Landsat most of the bands are having 30-meter resolution, but thermal band is having 90-meter resolution. Why? Because we discussed during that time that in thermal we do not have sufficient energy which can reach to the satellite. So that's why we have to increase our pixel size. So what I'm telling over here is, so the first of all, the correct answer is the fourth one, Landsat and NOAA. But I will just display like why. Just a minute, let me select my pointer. Yeah, so what will happen that in Landsat, if we take an example, so we have this 30-meter data set, and then the like 1 pixel is, so this is the Landsat data sets. So the first one is 30-meter pixel and the second one is a 90-meter pixel. So 90-meter pixel will cover the 9 different 30-meter pixels. So this is the visible band, like wherever we are using the reflected energy. So this pixel corresponds to reflected energy, and the pixel with a 90-meter resolution, it will show the thermal. So why we need more area over here? Because here you see energy will come like on the particular part which is 30 by 30 meter, and it will go back to satellite. Now when you recall, in thermal remote sensing we are capturing the emittance rather than reflectance. So what will happen that these pixels will absorb the energy, and then after it will emit during the night time or some other time. So what will happen that most of the energy is reflecting only. There is very few amount of energy which is absorbed by these 30-meter pixel. So whatever energy is going back due to the emittance value, that is very less. So whenever it is reaching to the satellite, we do not have sufficient energy which will go up. So that's why what we have to do is we have to do something so that the energy which is reaching to the satellite is high. So one thing we can do is we can increase the size of the pixel. Because of it, like it now it will give the area of 90 by 90 meter rather than 30 by 30 meter. So this is one way to increase the energy which is reaching to the satellite. And if you recall that Landsat TM and NOAA AVHR both are having this. So we'll just also see this satellite as well. So just share my. So just a minute, I will show it to you. Yeah. So So you can, if you just, are you able to see my screen first of all? Hello.
Yes.
Okay, okay. So if you see this thematic mapper, you can see this sixth number of band, which is having 120-meter resolution, and other rest of the three are having 30-meter resolution, and it is falling between 10.41 to 12.5. It means it is a thermal infrared sensor. It's like in 3 to 10, and its spatial resolution is high. You can see the spatial resolution of normal sensor is 30 meter, and then the thermal band is 120 meter. And then if you see current satellites like this MSS sensors in Landsat, then also you can just see the resolutions as well. And then now we'll see the Landsat current satellites. What is the change in the updated satellite? Landsat 8 and 9. So you can see now this is the entire wavelength of electromagnetic spectrum, and then here we are having the thermal infrared sensors, TIRS. So if you go down, like Landsat 7 is having the thermal infrared in 10.31 to 12.36 portion, which is 60 meter, and then panchromatic band, which we discussed earlier. So in that, it is 15 meter. And then you can see the range is also very high. It's like covering the entire RGB section and some of the near infrared as well. And in Landsat 8, if you see OLI sensors, then over here also you can see these there is two thermal infrared bands, which is at spatial resolution of 100 meter, band number 10 and band number 11, which is like they have divided into two different parts. So now what we will do is, so is that clear? And now we'll just see one more thing, NOAA VHR also. So in that as well, if we see, so you can see it is also sun synchronized satellite, and the range is 804 to 870 kilometer daily data it is giving. And if we go down, it's not showing here, but VHR band. Let's see. So we can see that in that also it is having some thermal infrared band, which is in that window only, around 10 micrometer. So two bands are there, 4 and 5th, which are useful for measuring sea surface temperature and soil moisture. So that's why these two satellite missions are useful for measuring the um, thermal infrared region. So is that clear?
Yes.
So main idea over here is that we have to increase the pixel size so that we'll get more amount of energy in case of thermal remote sensing. So the question one can ask is like, if we have same pixel from reflected energy or visible spectrum and thermal pixel also. So which pixel will be having more amount of size or which will cover more amount of area. So the image with the thermal remote sensing will have more amount of area if both are having same pixels. So now we will see some questions on map scale also. So a topographic map prepared by Survey of India covers 1 degree by 1 degree area on single map. So here you can see the map of India and they have divided that map into number of grids like this. So what we have to do is the minimum ground distance which can be represented on this map is fill in the blank. So here, first of all, the first division is made at 4 degree by 4 degree. So if you see the first division which you measure, so that is at 4 degree by 4 degree, which is known as a million sheet or a scale of it like 1 raised to million. So you can see here in the topo sheet, it will look like this. 1 million topo sheet, it is known as a 1 million topo sheet, and the resolution is 1 raised to 10 to the power 6, which will cover the area around 4 degree by 4 degree. And now how to represent that grid? So that grid you can represent with just a number. Let's say 65. So here when I referring the grid 41, it means it is covering the Gujarat region. 47, it's covering the Maharashtra region. Then we see further into the grid. So now let's say if we take the grid number 55, it will be subdivided into 16 parts, which will now become, earlier one it was 4 by 4 degrees. So if we divide into four equal dimensions, then it will become 1 degree by 1 degree. So now each pixel will have 1 degree by 1 degree area and total number of pixels will be 16. So that is the further classification that is known as a degree topo sheet. In that extent is like scale is 1 is to 2 like 50,000 and the extent is 1 degree by 1 degree. Then after, if we take any further pixel, let's say if we take D, so there is a further subclassification that it is classified into further 4 by 4 windows. So from 1 to 16, and then it will become now, if you divide 1 degree by 4 part, then it will become how much in terms of minute?
15 minutes.
15 minutes. Okay, so you will get the quadrant, which will be like 15 minutes by 15 minutes. So how to represent this grid as a 55D4 like that. So now this is the different scales. So these questions are like which are being asked in the GATE examination. In that you have to keep something in mind that if Survey of India map is just 1 by 1 degree, you have to keep in mind that what is a scale of that image and what is a minimum distance that you can show. So here, if we take
On
this, yes,
111 kilometer, that's
yes. So here, I mean, the answer is like 1 degree by 1 degree. That is entire grid will cover 1 by 1 degree. So it doesn't mean that the answer is 111 kilometer, but
no sir.
the map which you will see, it is having 1 by 1 degree. So for that like clarification, I will show you one of the image of Survey of India so that you get more clarity. So whenever you download any image from Survey of India or you purchase any image, it will look something like this. So are you able to see my image? Are you able to see it?
Yes sir.
Okay, so here you can see this is one of the topo sheet of Survey of India. Okay, now here they have written number G43S7. So if we see inside that, so here you can see G43S7. So we will see this G, it means G, like they have referred G as a first and then after 43S. So it's like it will be covered in this area somewhere. So if you just further see that you have the scale is written there, and here they have divided that into this specification guideline which we used as well, that it you can see 45D7. So this region 45D7, which will come over here, that 45, then D, and then 7. So it will come over here, somewhere here. Okay. Now you can see that grid we are representing. So when you download this kind of topo sheets, you can see the scale. You can see the scale which it is having. The minimum scale is also shown here, the maximum scale, the directions as well, everything is shown here. And then when we talk about that one image is representing 1 by 1 degree, it means that this length and width of this image is 1 by 1 degree. So here when we have scale of 1 raised to 50,000, then we can see that our image is 15 minutes by 15 minutes. So here 1 degree by 1 degree doesn't mean that 1 kilometer. It is just a maximum dimension of image. And then the scale given into that, we will find out the minimum distance, which will be like 1 degree map. It's having the scale of 1 is to 250,000. And then minimum distance is 0.25. So that information you have to remember. And then when we have 0.25, so if you convert that into 0.25 to mm to meter, then it will become 62.5 meter. So I will give you some time. You just recall this example one more time, because it's like very different. And what you can do is, like, based on this, we have one further question. So you just try to solve this question. So I will give you the 5 minutes. You just do that thing, and then we will discuss. I will just put my screen. So yeah, बोलो बोलो. नहीं नहीं चल रहा है. No, I can't. NPTEL. अरे ये छूट जाएगा तो मतलब कंपलसरी होता है इसमें, मतलब 9, 7 to 9. नहीं नहीं अभी कुछ नहीं हो रहा. सही है चंगा. बहुत. It was good only. फाइल आणि अंदर असं. इसमें इसमें. So are you done with the answer?
250 meters.
Okay, so no, meter, it will not come in meter. We just have to see how many number of topo sheets. So your answer will not be in meter or something. You have to say number. So here it is saying that we are having a map which is 55D12. Okay, so if we have this map, and then we will put this kind of map in a 4 degree by 4 degree, and how many this kind of map it will have. So it is 55D12. So we see 55D, and then in that also 12. Okay, 55D12. So now it is required. It is equivalent to 4 by 4 degrees. So this is main 4 by 4. We are dividing into D, it means we are dividing into 4 parts. So first of all, we will have 16 grids. Now we are seeing, like, in D also we have to go to 12 number. So we will further divide it into 16 parts, 4 by 4. So here we will have 16, and then further classification also for 16. So if we put 16 cross 16 maps together, then we will get one 4 degree by 4 degree image. So is that clear? Is this clear?
Yes, sir.
Both of you?
Yes.
Okay, so now we have the next question. that Survey of India topo sheet number 43D6. So here the number is 43D6, covers ground area of how much? So that you have to define, like from this only you have to find out. 43 it means this one, where is it? 43 is mean this one. Then D it means over here somewhere. So this D, when we specify like 43 is 4 degree by 4 degree. Now if we go to D, then it will become 1 degree by 1 degree. And then we have to further go down to 6 as well. So this pixel also we will divide into subpixels, which is 6. So it will come over here somewhere. So the main is 4 degree by 4 degree, further will be 1 degree by 1 degree, and then further will be 15 minutes by 15 minutes. So your answer will be this one. Is this clear?
Yes, sir.
Okay. Now we are having questions on the photogrammetry as well. So we discussed that when we have some two image, when we are capturing the photogrammetric images, we should keep some kind of overlap between the two images, which will help us to recreate the three-dimensional structure, or which will help us to create a relief and other estimations also. So now here it is given that longitudinal overlap is 65 degree and side lap is 20 degree. So if we have this much like overlap, and if you want to cover this much area, 12.8 to 8 kilometer, and then aerial like images which we are capturing is like having scale of 5 mm by 100 is equal to 100, and size of one photo is 23 centimeter by 23 centimeter. So how many photos are required? So for this, like we have one formula, this one. So here you can see the L1. Can you switch off your mic, please?
Hello.
So we have this formula with L1. So here L1 is the length of the area which we want to cover, which is 12.5. W1 is 8 kilometer. So length and width of the area which we want to cover. Then PL and PW is the overlap which we are having in the longitudinal direction and across the dimension, which is 65% and 20%. So like here it will be like, sorry, it will be like 20%, 0.2. Okay. And then we have, just clear it. So we have this PW by 0.2, and then scale is like 5 mm is equal to 100 meters. So if you convert everything into meter, it will become 1:20,000. And the length and width of the photograph is 23 centimeter by 33 centimeter. So now put everything into this equation and convert like all your units into meter, and then find out like how many photographs you will require if you want to cover this area. I will give you 5 minutes, apply everything into this formula and find out your answer. बताओ, देखा एक्सरे? पता नहीं, दर्द तो नहीं था बट ठीक है। हाँ हाँ, खा लिया मैंने, मतलब खाना तो अच्छा दे रहा है यहाँ पे, अच्छा दे रहा है। अभी आएगा खाना थोड़ी देर में, देखते अभी तक तो कोई डॉक्टर ने बोला नहीं है कि कब होगा डिस्चार्ज। तो अभी आज अगर डॉक्टर आते हैं तो ठीक है, वरना कल पता चलेगा। हाँ हाँ, वो अंकल के घर पे है, खाना खा के है। अरे मैं बोर हो रहा हूँ। आए थे ना ये लोग, यहाँ पे ही थे
So
लैब
is
वाले.
the answer 79?
No. So the correct answer is you just put everything there. In the first one, what you are getting, the first portion. So you will get 9 into 4. So 12.5 into 10 to the power 3. 1 minus PL, which will be like become 0.35. And 1 L, it means here it's L, not 1. So 23 by 100. And then you have S is equal to 1 by 20,000. So try to do this one more time. Are you getting the value or not? And then if you just get 4.1 or also like 3.1 or something, just make it to nearest integer, because images we will capture if like 3.1 is also coming, we have to consider as a 4, because here we do not have to see as a, like if 3.1 is coming, just consider it 3, because otherwise it will not capture image. So make the nearest like digit after that point. Like if 5.5 is coming, then take it to 6. If 5.8 is also coming, take it to 6. If 5.1 is also coming, take it to 6. So do it one more time, give it a try. Are you getting it or not? The main problem is you have to convert everything into meter. बारिश कैसी है इस कैंपस में? लैब वाले आए थे, पारस, निरंजन, राजेश भैया, अनुज भैया, उर्मिन भैया. हम्म. हाँ, उनको मैंने कॉल कर दिया था, मैसेज कर दिया था. बोले रेस्ट करो. नो. Did you get the answer? Hello.
Yes, sir, just a minute.
Okay.
The
Hmm.
first one is coming around, yes, coming is around 8.76, which
Yes.
is around
And then
9.
earlier, the next one will be like 3.1 or something.
Yes, sir. Yes, sir.
Okay. So yeah, so you will get the 36 numbers of AutoCAD. So now the next question is like, if the longitudinal overlap in aerial photograph is kept as a 65, and the common overlap, like which is also known as a superlap. The superlap is like same, like similar portion of 3 different images. So how much that will be? Like 3, if you take 3 successive photograph, what will be the superlap? So first we will have this kind of image. Then we will take the next image. Then we see that 65% area is becoming same, like overlap, longitudinal overlap. Now when we take the third image, it is having some overlapping portion with the first image also and second image also. So now we have to find out the superlap. Superlap, it means the area which is becoming similar in the all the three image. So if we take, we have to just find out this particular part. If you see, so if this is
That
65,
around 27%.
no, it will be like in the this 27%. No, so see, if this is 65, then the rest of it will become 35. Okay, so if we take this as a, if this portion which is 65, then the next one will become 35, because 65 35 will make 100. Now when we see this portion, like how much it is, so we will just deduct 65 minus 35, which will become 30. So is that clear?
Yes, sir.
Clear. So we have to find out the superlap, which is a common area of three successive photograph. So now the next one is how many number of cells of 30 meters spatial resolution would be required to cover a 1000 1 raised to 50,000 topographic map of survey of India, assuming that it's having 1 minute is equal to 1.85 kilometer. So first of all, we have to find out like if it has having the dimension of 1 raised to 50,000, then what will be the, so earlier we like learned that if we having 1 raised to 50,000, so in the earlier map when we are discussing that maps, so here we see then if we have the 1 raised to 50,000 dimension of map scale, then it will cover the area of 15 minute by 15 minute. So this 55 d 12 like that. So what they are asking is, if the map is 1 is to 15,000, so the extent will be 15 minutes by 15 minutes. So if you want to cover that 15 minutes by 15 minutes with the 30-meter pixel, then how many pixels you need for that? So what is given over here is, so here they have given us that if we have this particular big chunk of image and the dimension of this image is 15 minutes by 15 minutes. So first of all, we have to convert that from minute to some linear units, let's say meter or kilometer. So we will use this relationship which is given over here, that 1 minute is equal to 1.85 kilometer. And then we will convert this 15 minutes to, so what will be the answer for that? 15 into 1.85. So 15 into 1.85. So that we will get the length of that particular like one side, that will be in kilometer, and then we will convert into meter as well, so we will multiply it with the 1000. So now you have everything in meter. What we have to do is we have to convert it into 30-meter pixel.
So
So
the
what
answer
we
will
will,
be the first one will be the correct answer.
yes, so you got the procedure like how to do it.
Yes, sir.
Okay, okay, fine. So you will get 855,625. So then we have this color composite. So we just have two kinds of color composite: true color composite and false color composite. So true color composite, it means when we superimpose RGB band as a RGB band similarly. So R in R, green in green, blue in blue. So that is a standard true color composite. So this statement is true. And when we have false color composite, that what we are doing, we are putting the near infrared band as a red, red in green, and green as a blue. So this third statement is correct and the other two are wrong. So is that clear?
Yes.
Okay. Now we'll go to the next question. So you have this like elements of visual image interpretation. So in that, which is the primary and which is the secondary? So when we see any image, what will be the criteria that we will see first?
So first we will see the first one is the correct.
Yeah, first one is correct. Then anything else is correct. So if first one is correct, then second one will be automatically wrong.
The third one might be.
Third one is also right, because texture means how the frequency is changing, tonal changes are happening. So this third one is also correct. And the
Yes.
fourth one is incorrect. Now we have two images. One is with 80-meter resolution and the another is 20-meter resolution. And both are having 512 by 512 pixel. So choose the correct option.
So Q, the option C will be the right answer.
Okay, minor details will be more in the Q. So that is right compared to P. Apart from that, anything else is correct?
Then option A also.
Thank you. So I told you that 80-meter with same pixel is there. So 20 into 4. So we'll get
That's
how much?
it will be
A or
16
B?
times.
Exactly. So it will become 16 times because we have to consider both the side. So 4 into 4, it will become 16. So option B and C is the correct one. Now, instead of this question, to trick then they will ask you, you have Landsat series of satellite, Landsat 8 or Landsat 9. And in that, satellite image P is image from visible spectrum or reflected energy. Visible spectrum, and then image Q is from thermal remote sensing. So find out the correct option. So first of all, you have to write down the value because they haven't given the value as 80 and 20. So for visible, what will be true? Like it will be 30 meter. And for thermal, what will be true? It will be 90 meter. So first of all, you have to find out these numbers. You have to remember these numbers because these are popular missions.
Yes.
And then you just find out the correct answer according to this. So it will become the opposite one. Is it correct?
Yes, sir. At least the chronology of their wavelength.
Okay. So now we have this next question, which is like on hyperspectral images. Okay. So what is true? We'll call you up. So what is like true for these hyperspectral images?
The bandwidth is narrow.
Bandwidth is narrow. So this option number one is, B is right.
A number of bands.
The number of bands are more.
Yes, we have 100 numbers of bands. So this option C is also true. And the second thing is number of bands are high. So we have a representation of band from each and every wavelength. So it means that bands are continuous in nature. So the option A, B, C and D, all the three are correct.
So I have a
So this,
question related to the
yes,
exam. Sir, in this assignment sections, if the three options are correct, if we choose two, they give us 2 out of 3 marks in the assignment sections. What about the
yes, so
exam?
they will deduct the partial marks.
And what about the exam?
Yes. So it depends on the pattern of exam also. If gate is there, they will be having different criteria. In this NPTEL assignments question, if three answers are correct, if you select just two, it will deduct the, like, if question is like 1 mark, so it will be like 1/3 marks you will lose, like you will get 0.7. Fine, is that fine?
Yes, sir.
Okay, now we have to see like number of cells required to cover 9 square kilometer area. So our image is 9 kilometer. So it's like entire area of the image is 9 square kilometer, 9 kilometer square. Now we want to cover that with the pixel of ester GDM. So how much pixels it will take? So first of all, we should know what is the resolution of ester GDM. So it is 30 meter. So now if we know that, we will divide like 9 into 1000 into 1000. We will convert from kilometer square to meter square, and then divide it by the like area of 1 pixel. So we will get total number of pixels required. So now if I say that here instead of it, I need MODIS satellite. So here I will tell that if the image is MODIS, satellite is MODIS, then how many pixels will be there? So first of all, what is the spatial resolution of MODIS? You can search also. So MODIS satellite is having a resolution of how much? It is 250 meter. So MODIS is 250 meter. So now find out for this how many pixels are required.
Just around 1.
Hmm?
So, 1440.
Yes, so like we just put 250 over here instead of 30, so it will become like directly like 250 fours are 1000. So similarly you have here 4, so 4 into 4 into 9, so you will get 144. Okay, so now the next one is to visually distinguish between the river channel and canal. If you have river, you have canal. So river will be like this, and canal will be like this. So if you want to distinguish between these two features, which parameter is useful?
The shape.
Shape. Okay. The size may be similar in the both the case, but shape might be different. Tone, because it's water only, so tone will be also same. Texture will be also same because it will not change like water. So the shape is correct answer. Now the next one is inactive remote sensing. Uh, of the Earth objects from the satellite-borne sensor, the source of energy used for sensing is lies at. So where do we put
Satellite.
satellite? Obviously, so sensor will be put over the satellite, and that will give us the energy. Now the next one is which of the following cannot be used as a visual interpretation key for satellite images. So which of the parameter we cannot use for this image interpretation? So you know texture, you know pattern, you know association.
The
But have you heard
projection.
about projection? Okay, so projection, it means how you are converting your three-dimensional map into two-dimensional map. So that is like projection. So there is a coordinate and projection and coordinate systems. So that is not useful right now because it will not say anything. So the now next one is the ratio between the reflected to incident energy. So if you have some surface like this, so whatever energy is incidenting, like incident energy, and then reflected energy. So reflected energy, and then this is incident energy. So the ratio between the incident energy reflected to incident, so it means R by I is known as a
Spectral reflectance.
spectral reflectance. Spectral reflectance. and then units of the spectral reflectance will be like, now energy is hitting the surface. Okay, so if we want to see like energy, so it will be like energy incoming, so it will be watt and how much area it is covering, so watt per meter square. And then we are saying the word spectral. Spectral means in which spectral band we are considering it. So it will be like micrometer also. So correct will be like watt per meter square per micrometer square. And then here when we talk about this object, is a three-dimensional object. So we have to consider a cone which has the unit of steradian. So meter square is from linear area, and this if you want to consider the three-dimensional, because whenever energy is incidenting on the surface, it will be like three-dimension, not the two-dimension. So we have to consider the steradian also. So it's like just a cone. So we'll show you how the steradian will look like. So you can see this kind of cone, which is known as a steradian. So if we take three-dimensional area, this cone is known as a steradian. So this energy will be like watt per meter square per this angle, which is known as a steradian, divided by particular wavelength. So it will be micrometer square. Oh, sorry, micrometer inverse. And now the next one is okay. So now the next one is when we consider about the sun synchronized satellite. So the sun synchronized satellite, which of the following option is true? So here you can see the sun synchronized satellites and the geostationary satellites. These are also known as a near polar orbits. So it's at a passing like it's polar, North Pole and South Pole. So first of all, they are near polar orbit satellite, sun synchronous. So that is true, which you can see over here only. Then they cross the equator at different longitude at nearly
Yes.
the same local time. So if you see how this satellite is moving, then it will like cross the like different location at the same time, different longitudes. Then they mainly maintain nearly the same sun target geometry while crossing the equator at different longitudes. And then inclination is less than 1 degree, so that is wrong, because here you see if the inclination you will see with the equator, this inclination is like around 90 degree, so around 89 degree or 90 degree, something like that. So this last option is incorrect, other three are correct. Now you have the spectral reflectance curve, which is like for three materials given, material A, B, and C, and you have three bands, band X, band Y, and band Z. So you have to see that which of the following statement is correct. So first of all, each of the curve is the spectral reflectance of the respective material. So that statement is true only because
Yes, sir.
it's curve and it is representing at wavelength what is the reflectance. So the first option is right. The second one is a sensor designated for the wavelength band Y will be best distinguish these materials in the image. Now if we see Y, these
Yes,
three
sir.
objects are separatable. Okay,
That's also true.
so that is also true. Now a sensor designed for the wavelength band Z will be best distinguished. So it's Z, if you see, there is no difference between all the
That's
three objects.
false.
They behave similarly only. So this option is incorrect. And the last one is these curves are normally produced using the spectroradiometer. So that is true.
This is
If
also
you have
correct.
this, yeah, so if you have this continuous curve that are using spectroradiometer, if you have a specific point like just line joining, then it will be from the satellite remote sensing. So option B, A, B, and D are correct. Now the next one is like choose the correct option for micro remote sensing. So partial resolution of passive micro remote sensor is coarser than the active microwave remote sensor from the same platform. So what you have, passive versus active. So in which one the resolution will be high? So first of all, microwave means the wavelength will be high. So here what will have, as we go towards the higher wavelength part of the electromagnetic spectrum, the energy which is being reflected is becoming less. And that's why when we have passive energy which is coming from sun, that will be less compared to the active sensors. So because of that, this passive, if we want to get distinguish some feature or we want to detect something, we have to increase the pixel size in the passive microwave sensors. So passive will have coarser resolution than active. Similar concept that we used for thermal remote sensing. And then the intensity of the signal written by an object depends on the geometry as well as the dielectric property. So yes, microwave depends on both of this. So the A and B is right. Then it is possible to see through the dense forest canopy. So that is also true. So it is possible to see the under the canopy, but not using X band. It is using the L band or some other band. So that's why here this band is incorrect. Otherwise, you can see through the microwave remote. So it's like see through forest using microwave, but the band which they have specified, that is wrong. So you can just like we can search the microwave remote sensing bands. So we will search these bands which are available. So you can see this is the first example. So you can see this. If we have this L band, then it can penetrate through the forest. But if we have X band, it cannot penetrate through the forest because the wavelength is 3 centimeter only. Here the wavelength is large, so it can directly go to the under the forest. Similarly, how this uh, micro remote sensing will behave for different objects like vegetation, alluvial soil, and dry snow or ice. So that also you can see it from here. And these are the like different bands which are available in the micro remote sensing region. So this is known as a KUXCSLP. So they have given this kind of nomenclature that so that to avoid the confusion during the military time. So this just do not have any meaning. So it's just to decode it easily during the wartime. So now we will see the next one. So this option might be correct if they have written L band over here. So now the next question is, when you have a sun and earth, consider both as a black body radiation. So which one is a true? So first of all here in the question you can see there is a, we have to find the energy in terms of wavelength. So you have to find out the equation which is representing temperature and wavelength. So that is Wien's displacement law. So this is known as a lambda max will be 2989, or you can just write say for sake of the simplicity 3000, or if you want to write specifically you just 2989 divided by temperature in Kelvin. So the answer you will get will be in micrometer. So first of all you will put the temperature as a 6000 Kelvin, and what will you get? For the sake of the simplicity you just consider 3000. So what will you get if you put temperature of sun?
Said that 9.3 micrometer dust lies between the two ranges.
What? So it will be divided by 6000. So how much wavelength we will get here
Sorry, sir.
in case of sun? Point
Point
5.
498 and point another is
It's fine.
point
And,
996.
yeah, and another one is for in the case of earth we will get around 9 or 910. Okay, if we put 300. So sun emits maximum energy at 9.3. So that is wrong because if we put the temperature of sun, we will get answer as a zero point 0.5 micrometer, not the 9.3. So if we want to correct this statement, we have to write earth there. Earth emits maximum energy at 9.3, or else sun emits maximum energy at zero point 0.5 micrometer or 4.9 something. So this option is wrong, first of all. Then sun does not emit energy at microwave. So that is also false. Sun emits energy at every wavelength. So that is also wrong. So is it right or wrong? Sun does not emit energy at microwave. First of all, what is the energy which you are getting from sun? What
Solar
is
energy.
that? It's a 0.5. So it is not falling in the microwave region. So these options are incorrect only. Then the wavelength of the energy emitted by the sun are a subset of the wavelength emitted by the earth. So okay, earth will specify like that is not true. The wavelength of energy is emitted by sun. So sun will like emit something else and earth will emit something else. So they are not subset. If you see the both curve, it will be like this much. This is for sun, this is for earth. It's not subset. Earth does not emit the energy at green wavelength. So that is true because Earth emits at 9.3. So we will see this for clarification. This questions in um, Sun and Earth like body. So you can see. So Sun is being picked around zero point 0.5 micrometer, and Earth will be like around 10 micrometer. So you can see the different plots. Like it is not a subset of it, and then it falls under the microwave region, whatever the Earth is representing. And you can see this is the visible portion where the earth is emitting more. So earth is sun is emitting more at 0.5, which is falls under visible spectrum, and for earth it is like under this window, which is microwave region. So is that like, did you get the point here?
Yes, sir.
Okay, so now we will see the another one. Which of the following is a map published by the Survey of India?
The topographical map.
Geographical. Then hyperspectral sensor consists of. So this is the same question, like but in the different format. So large number of wide and discrete band. So it will not have wide; it will have narrow
Large
bands.
number of narrow and contiguous band.
Yes, so narrow and continuous bands. Then the next one is the wavelength at which maximum energy is radiated or emitted from the forest fire. Now forest fire temperature is 700 degrees Celsius. So use the winds displacement
It will
rho.
be around 3 micrometer.
How much? See here, temperature is not in directly Kelvin; it's in
So
degrees
I
Celsius.
have to add 273 there.
Yes, yes,
It will be
exactly.
around 1000 and the 3000 upon 1000, so around
Uh,
3 micrometer.
so it is like gate question, so you have to do proper calculation here because they have considered the round off to 1 decimal point only. So if you have normal options, then do that. Otherwise, if this kind of writing question is there, then you just have to do like this. So you will do and then you will get. Yes,
2.9784.
yes. So now the next one is you have to like join this column A with column B. So first of all, like which one is true according to you? So we'll go with the here like 242 bands are there. So which is the satellite having 242 band? Is there anything specific is given? So what do you say? Which satellite will have 242 bands? That is 242. It means more than 100. So which is like hyperspectral. And then we discussed a few times back only that Hyperion 1 is the
Yes, sir.
hyperspectral image.
Hyperion EO1.
So yeah, so the S will be 5. So from that, this either C or D will be correct. So Q will be like 3. So line set TM is across the track scanner. And then we just have to specify either P or R.
Modi's have
So
18 bands.
these have 18 bands. Okay, so the R is fourth one. So the correct option is D. Sorry, Modis will have Sorry, MODIS will have 36 bands, not the 18 bands. It is having 36 bands. We'll see. MODIS 36 bands. MODIS bands. So if you go to NASA MODIS site, you will see how many bands it is having. So you can see it is having band number till 36. So that option like MODIS 36 bands. Okay. So R will be
Okay.
like 1. Now the next one is you have to just see the units of a given quantity, like variables. So which one will be the true?
So radiant energy in joules.
Radiant energy will be in joules.
The reflectance will be on the watts per meter square.
Reflectance will be dimensionless because it is a ratio.
Yes, sir. Yes, sir.
Okay, so it will be dimensionless. So S1, and you are saying that this radiant energy will be joules. So Q will be 3. So this option D will become right.
Yes, sir.
So just wait for 5 minutes to solve this question. So now you will say this one. So like which one is correct for the satellite image interpretation? So which band is more sensitive to moisture and soil, like vegetation?
So option B and D are correct.
Option D and
D, B and D.
D. So green band is useful to discriminate between the cloud and snow. That is true. Blue band is not useful to discriminate between water and snow. This is also true. Then SWIR band is sensitive to moisture in soil and vegetation. So that is also true. So now you can see this option is like green band is useful to discriminate between the cloud and snow. So we'll just see the here why it is wrong. So cloud spectral signature. So it's like you have to uh, like remember the key property of the objects. So if we see this kind of thing, so you can see here that snow and cloud is there. So snow is red and black one is cloud. So if we see this thing 0 0.4 to 0.6, because in the question it is given, we just take this image. So like this if we have, so here you can see green band is useful to discriminate between cloud and snow. So green band like lies over here 0.5 to say. So in that like this is not that much clear between snow and cloud. So that option is wrong. Then you see near infrared band. So that will be over here, this one after 0.8. So near infrared band is useful to differentiate between land and water. So land is like, you can see this land and water. So like basically barren land, it will be have more compared to water. Water is having nothing, whereas barren land will have something over it. So that option is right. Then blue band is not useful to discriminate between water and snow. So blue will be over here only. So water and snow. So you can see blue band is not useful. No, it is useful because if we have blue band, we can differentiate between water and snow. Snow is having high reflectance in blue band, whereas water is not having anything. So blue is useful actually. And then SWIR is sensitive to moisture in soil and vegetation. So you can see this infrared region. This is infrared region, which is like having more values in the case of vegetation. So like you have to remember those kind of spectral signature curve for proper objects, which will help you to distinguish. Is that clear? So earlier one we showed a similar example, but there just three bands were given. But here you have more classes and actual data. So is it clear?
Yes.
Yes,
Okay. Now we have next question that map A represents all the road, street lights, tree and building of the campus within the 5 km square area. And then the another map is representing forest and agriculture area in the 10,000 square kilometer area. So considering the physical size of both the maps are same, which of the following is correct? Here in A we have much more details. So scale of map A is less or high. So in A we have more details. It means scale is high for map A
Yes, sir.
compared
Option
to
A and D.
okay. Then after both maps are at same scale. So we are saying that it is having large scale. It directly means that they are not both at same scale. And both maps are not at same scale. So DU will be also right. Now we have water body appears in dark in near infrared region because what water do?
Water reflects. Sorry, water
Absorbs.
absorbs.
Exactly. So water absorbs most of the radiation. That's why we know water. Then the approximate altitude of this polar sun synchronous orbit of ISRO satellite. So this will be like how much? So we have seen something like around one. We just see some satellites few time back. So what was that? Around. So it will be like greater than 400. So we have seen one right now in the class, which is around 838, something like that. So now we have satellite image with a 6-bit radiometric resolution. So if we have 6-bit radiometric resolution, what will be the gray levels or radiometric resolution?
64.
64. Okay. So now you have learned about this kind of sensors. Sensor, it means that they are detecting energy from the, like it is mounted on satellite and which is detecting the energy. So if we have sensors, which one is correct? So there are two types of sensors, whisk broom and push broom. In whisk broom sensors, um, what do we have is that it will scan like this. So it will divide into different segments and it will do like this one by one. So one, then this one, then this one. So this broom will like go like oscillating like this, like this, like this, like this, like this, like this, and it will cover entire area. So that is known as a whisk broom. And push broom, it means will like just have oscillation is this direction along this sky. So it will be this like this direction swing. So at a single time it will cover all this thing, all the red dot which we red area which you are seeing. It's single time it will cover everything, whereas here in single time it will select this much only. So now if we take this thing, so which one is correct? Just the two options are there. Just find out which one is correct. So here we can see that on satellite sensors will be there. So we have how many detectors? 3,000 detectors are there, which is light over here. Now swath on the ground, it means how much area it is covering. So this area which you are seeing over here, that is 30 kilometer, and this is the amount of sensors which are available. So what we will do, the area which is 30 into 1000, and then divided by number of sensors which are available. So there are 3000 sensors which are mounted on this satellite. It is covering this much area, which is 30 kilometers. So if we divide 30 kilometer divided by this number of detectors, we will get 10 meter. Is it correct? Did you get the point?
Yes, sir.
Okay, so now someone will ask you the backward question that if the number of like detectors are 4000 and ground swath is 20 kilometer, then what will be the spatial resolution? The same question. Now what will be the answer? So what will be the answer over here?
So 5 meters.
Yes. Right. Now, so what will be the answer over here? Is similar only. So like number of sensors are 4000 and swath is 20. So 20 kilometers. So 20 into 1000 divided by 4000. So you will get around 5. And now you have the next question, which is for push broom sensors. Is something like this. So what is the time to collect 1 pixel? So if it is covering like this, the time which it takes to cover 1 pixel, that is known as a dwell time. And what will be the time for this? So here the option like details given is field of view. So this is the field of view is 2 degree. Then the field of view of this instantaneous field of view. So here like 4000 sensors or 3000 sensors will be there. So for each sensor, the field of view is 1 milliradian. And then time to scan one full scan line. So one full scan line will take 2 into 10 raised to minus 2. So how much time it will take for single pixel? So did you get the question first of all?
Sir, have I to convert the degree to radian?
No. So here it's like conceptual question. See, in push broom sensors, how it will collect the data, all data at a once. Okay, so this entire line it will collect in just one go. So it doesn't matter that it is collecting a data of one line or one pixel, because it is collecting it's at the same time spontaneously, like it's in just one go. So whatever time it's given here, 2 into 10 raised to minus 2, it will be same only 0.02, because it is covering an entire thing it's once only. Did you get my point?
Yes, sir.
Okay, so this is like tricky question. They have given you so many details to just confuse you, but just to use the concept. Here, if it is like this case, you have to do something to get the answer. So this is like questions which we discussed. So we have covered the all the questions from GATE question paper from 2020, 2023, and 24 on the topic of geomatics engineering. And like this is the questions they asked on the topic of remote sensing and photogrammetry and maps. So first of all, like what is your view on the questions which are asked in GATE and what you do in class? So what is the level of questions? So are you able to solve these things?
The questions are not that hard, but still
Yes.
memorize some things.
Yes. So you have to memorize something, basically some popular satellites resolutions. Then some questions you have seen on map and scales. So in that survey of India's map, you have to remember like what each map will, what will be the scale associated with that, and also and so forth. So anything else like you noticed? I mean, whatever question you see in your assignments, it is like difficult than that, or not that difficult, or
No, sir, not that difficult at all.
and you just seen that one thing also, that you here the amount of memorization is less compared to the questions which you see in assignment. Hmm?
Yes,
So I mean, you can see like how much questions can come in the examination from the concept which we learned till now. So now in the next week, what we will do is we will take the questions on GPS, because next week will be like on you will doing the GPS surveying. So all the questions related to GPS we will solve, and meanwhile we have some time now. So I will show you some of the popular satellites if possible. My wavelength. So we will see this site which I told you yesterday, like last week also, that this Sentinel Hub EO browser. So are you able to see my screen?
Yes, sir.
Okay. So here, I mean, if you go to any area, let's say I went to Gandhinagar area, you can see this kind of image, satellite image. And this resolution of the Sentinel satellite is 10 meter by 10 meter. Now, if you see, now you know the difference between true color and false color. In false color, if you select, how will it look like? It will look like something red, because you are representing vegetation. So you will see more color as a red color. So you can see now how it looks like. So did you get an idea about true color and false color from this?
Yes.
Apart from that,
Yes, sir.
if you want to do anything for any band, like here we are just using RGB and near infrared band. But if you want to put any band, like let's say any band, so what you can do is you can go to this button, like just click over here, and then you can just edit it, and you can see the composite. So which band you want to consider as a R, which as a G, and which as a blue. So this is the normal RGB. If we consider 2 as a blue, 3 as a green, so this is like actual RGB. So red as a red, green as a green, blue as a blue. Then you will see true color composite. Instead of it, if you consider 5 as a red, which is near infrared, red as a green, and green as a blue, then you will get standard false color composite. And further on, you can take any of the bands which you want to display. So you can select this, like try with this website. You can just check out like how the different bands will look like. So you can try this thing. And then we have seen the indices also, like NDVN also. So that also you can create over here. That band 4 minus band 3 divided by 4 plus 3. So something like also that you can provide, and you can specify the threshold of it from -1 to 1. So you can try to explore this portal further. So now we will see some of the popular data sets. So for that you can go to site of Google Earth Engine. So they are having data catalog, like whatever the data. So this is a cloud-based remote sensing platform where you can analyze the different imageries. All the data are stored by Google. So you can just see like what amount of data is given over here. So here, if you see this catalog, you can see like popular satellites are Landsat, MODIS, Sentinel. So these three are very common one. And if you go down, you can see the satellites which are useful for surface temperature, surface satellites which are useful for climate data, satellite which are useful for atmospheric weather phenomena. So this how Landsat will look like. So if I will click on Landsat satellite, so in that also you can see Landsat 9, Landsat 8, Landsat 7 ETM plus, Landsat 5, 4, 1 to 5. So all the sensors are given. Now if I will click on any one of it, it will show me which product you want. You need surface reflectance or top of the atmosphere reflectance or raw image you need. So I will click on, let's say, surface reflectance. So what is reflecting back from the surface? And then once you, it will show the description of that image. You can see the swath width that one image will cover 170 kilometer by 183 area. Then it's like different, like what is the specification of this data sets. Then if you go to band, it will show you the wavelength which it represents. Now the what what is the resolution of this band. So you can see resolution is 30 meter, and then this maximum value will show you the radiometric resolution. So it's 65,000. So you can show from 0 to 65,455. So 456. So it is equivalent to how many bits? 65,456. So this is around approximately how much? So if we take 65,456 radiometric resolution, how many bits it will have? Yes. So you can find like that 2 raised to n is equal to 65,000 something. So further, like now if we see the different satellites as well. So now we have this Landsat 9. Now if we see the other one, that's a Landsat 125. No, no. So you can see here Landsat 1, 2, 3 are also available. For how much time it is available, 1975 to 1982 or 78 to 1983. So you can just click on like we have one question on that Landsat 3's temporal resolution. So we can just go and check out the temporal resolution over here. You can see this partial resolution is 60 meters, and then for one band it is 30 meter. And you can see, if you want to see some further thing, you can go to the description, you can go to image property. So how much cloud cover it is having while capturing the image, cloud cover on land, then collection numbers. So different kinds of thing you will, like variables you will get, and how will it look like when you consider the actual remote sensing imagery. So this is about the Landsat satellite. Now we will see something on Sentinel. So we'll go to Sentinel, and now in Sentinel we have Sentinel-1, which is micro remote sensing data. Sentinel-2 is multispectral data, and then Sentinel-3 will be like ocean, for ocean color monitoring, and Sentinel-5 will be for atmospheric variables such as carbon monoxide, ozone, methane, and so on and so forth. So Sentinel-2, if we go multispectral instrument, it have this surface reflectance value. It's available from after 2017, and you can see like description. So it is having the 16-bit radiometric resolution, and then bands, you can see it is having around 12 bands, pleasure bands, and then further depending on cloud quality control bands. Then resolution of some bands is 10 meter, like blue, green, red is 10 meter, and then near infrared is 10 meter, and rest of the bands are at 20 meter resolution. Aerosol band is 60 meter, and then this band 11 is also SWIR. Sorry, water vapor is also at 60 meter, and you can see like water vapor, which region of electromagnetic spectrum they are using it. So if they will use this particular wavelength, they can detect the water vapor properly. That's why. So this is about Sentinel. Now this is the micro remote sensing data. So active sensors. So in that you will have the not reflectance but scattering, that will measure as a polarization, like HH polarization, HV polarization, VV and VH. So how much backscattering is happening, that units will be in decimal, and that at 10 meter resolution. Then we have this Sentinel-5, which is for tropospheric measurement. So you can see the aerosol optical depth or cloud and something. So that you can also see that is at 1000 meter resolution. And property, you can see this kind of property they have. Bands. So these bands are the sensor altitude at which altitude the sensor has, and then azimuth angle, zenith angle. So all those details will be there. And then rest of the satellite data you can explore. Now we'll see the last one, which is Modi's. So Modi's, if we see, the resolution is 250 meter here. So if we select this Modi's Terra and Modi's Aqua, Terra is for acquisition on ground and Aqua is for acquisition on water. So that is available for 250 meter also, 1 kilometer also. So you can see this thing, just to click on that. So you will see this kind of bands which are available. And now if we see other like high resolution data sets, which we like in questions we have saw something. So you have this planet data set, which is planet sky. So this is multispectral image. If you go there and if you see, this is at 2 meter resolution and the panchromatic band is at 0.8 meter resolution. Then after, if we see this NAIP agriculture data sets, so this data set is at 0.6 meter. Then this other imagery, so this is also at 0.1 meter resolution. So now if we open this kind of imagery, so how will it look like? I mean, once we want to open something which is very high spatial resolution, let's say 0.1, how will it look like actually in image? So if you are interested in satellite data processing, you should learn this Google Earth Engine platform. So now you can see this how this 0.1 meter data will look like. So you can see each and every road, each and every tree, the shadow of the tree, how it will look like. So every minute detail you will get it, but it will cost a lot to collect the data sets. Similarly, we have, so these 4 data sets are there under high resolution data sets. And then we have some other data sets also. So you can see geophysical data, land cover data. So these are the product after processing the remote sensing data. They generated the croplands or land covers or terrain. So this kind of data you can visualize further, like what is climate data. Okay, so this thing you can find out. Now we will see. So is this fine? I mean, everyone is now comfortable with this data catalog. I mean, you can just open it and see in your system as well.
Yes, sir.
So I will give you 5 minutes so that I will just put that site over here first of all. So what you can do is just open this site and see by yourself like all these data sets which are there. So I'll give you 5 minutes. We'll meet at around 43 or 44. You just go through the various data sets and just see like their properties. If you didn't get anything, just get me back, because this is like very high amount of information which I'm giving. So I'll give you 5 minutes, just look at into every data. Hmm? सात now time अभी सोमवार So are you done with hello? So are you done with checking the site?
Yes, sir.
Okay. So now what we will do is we will cover one more site which is quite handy to collect the remote sensing data set if you want to download and just analyze easily. So name of that site is Climate Engine. So you can write Climate Engine on your Chrome or any browser. Then you can click on login. So are you able to see my screen now?
Yes, sir.
Okay, so then you click on login and then you have to log in through your Google account, or you just, if you do not have any account, then make an account. So, so it will open a site. The internet is not that good, so it will take time in opening it. So once you will open this site, it will look like this. So over here, it is taking time, but map will come and here the different variables will come, and you can generate two types of data over here. You can generate map or time series. So first we will close this, and we can find out like which data you want to generate. So if we want to generate, let's say we want to find out the rainfall happening in India, let's say some portion in India, what was the rainfall in the last month, or like this JJS season at Gandhinagar or something, let's say. So if I'm here in Ahmedabad, let's say, so what will be the rainfall in Ahmedabad in the last 3 months or at some time? So I will select my data. So I want to create a time series. Point I have to select. So I will just either create point or polygon. So I will just draw a polygon over Ahmedabad city like this. Now you have to select the variable. So I want to collect the data related pertaining to climate and hydrology. So I will select this climate and hydrology, and then after I will select this, let's say GPM. This is the global precipitation measure data sets, which is at 11 kilometer resolution and daily data sets. And this is available from 2000, 1st June of 2000 to 1st June of 2024. This data is available. So let's say it's not available in this range, but let's say I want to see that what happened in the last June, July, August. So how was the rainfall in last June, July, August month? So it's from 1st June of 2023 to 31st August 2023, and I will click on get time series. So it will generate a time series of rainfall like this. Similarly, instead of rainfall, you can see it is going till 150 mm in the month of end July, 22 July. Then after you can see the different variables also. So if I select this remote sensing data, you have this Landsat 5, 6, 7, 8, 9 also, Modi's satellite also, Sentinel satellite also, VIRS satellite also. So you can select anything, any parameter, and then any variable under that. So you can see the value in a green band, value in the near infrared band. So that will be useful to construct the spectral signature as well. So basically, we will talk about this climate data only as of now. So I will select now ERA5 land data set. This is the reanalysis data, which gives you the all the climate parameter at 11 kilometer grid. So we can use minimum temperature, maximum temperature, mean temperature. So you just click that variable and then click on get time series. So it will generate the time series of temperature. Now you want to plot minimum and maximum temperature both on same plot. So instead of one variable analysis, you can provide two variables. So in second variable, I will select this ERA5 land only, and instead of mean temperature, I will select the minimum temperature, and then last JJS. So you can find out the correlation between these two also. So in both I have selected minimum, but one I will select minimum and one I will select maximum. So like this, you can see the minimum temperature is not changing much, whereas maximum temperature is fluctuating a lot. So now what you can do is use this site and generate this kind of plot for precipitation Tmax and Tmin for your area. Where do you live? I mean, to generate for last JJS month. If you take a larger area, it will take some time because it is capturing, like covering the data, processing everything. So consider just a 3 month. So it will like be quickly. So now generate the data for your study area or any area you select. And once you are comfortable with it, we will end this lecture. So try to do it by yourself. So go to this site. I mean, all of you got the site, or should I share the link?
You can see our picture.
Okay, sure. So is this exciting? I mean,
Yes, sir.
so you can see the different data sets from here. So just create an account in that website and download and make a time series of any data. And if you want to create maps, then go to the map section rather than time series. You can just click on this map button over here, make map, and you can generate map also. And in make graph time series. And you can see like various YouTube videos of also available of this particular climate engine, where they have discovered the various applications in drought, flood, how you can use this ready to available data set through case study. You can, if you are interested, you can look into it further. So now just do it for your study area. Generate a plot with Tmax and Tmin for any two variable. Tmax and rainfall also you can do. If you get any problem, then just tell me. Are you both able to do this thing?
Yes, sir.
Okay, so now we'll see one insights which we are getting from this plot. So if you see this Tmax and precipitation, so what you can observe here. So after downloading or plotting the data, next thing you have to make decisions. So what is happening here?
We can, sir, find out. We can actually distinguish the rainy season among this chart. The
That is
typical
fine, but what is
geometry.
happening with rainfall and Tmax?
When the rainfall spikes, the temperature uh, goes
Gets
down.
low. Exactly. So during monsoons, as we are going in the monsoon season, the temperature is decreasing because of the evaporative cooling which is happening. So rainfall is coming, and because of that, evaporation will it will cool the air basically, and because of that, the maximum temperature will go down because of that reason. So whenever you have higher rainfall, your temperature will go down very well. And you can also feel this thing on ground when you have higher rainfall, you will see the very cold temperature, or like it will make you feel cold. Similarly, this correlation between this rainfall and this temperature is negative. Similarly, if you use this rainfall and T mean, so what will be there? Like there will be no relationship between these two parameters, or if it is, it's very weak relationship. You can see it's not changing that much compared to Tmax. It's also decreasing, but it's not that much. Okay, so like that you can take the decisions. Now you can plot the NDVI, and also like with this you have plotted rainfall data, and you can plot NDVI also. So NDVI will show the greenness of vegetation. So with rainfall, whether your vegetation is becoming green or not. So if it is not becoming green, it means rainfall is occurring in another area. So if you do not have rainfall, then also if it is becoming green, it means you are providing water through canals or other source of moisture or other source of water for you by doing irrigation. So like that, you can think about various things, and you can generate the insights from that. So with this, I mean, we will close today's lecture, and uh, now our remote sensing section is almost over. So we will have some now next week we'll have the questions on GPS, and then further on GIS and other things, advanced thing. So do you, if you want to learn something in remote sensing further, you just let me know in our comment box or question answer box. If not, then we will start with the GPS section from the next lab. Is it fine?
Yes, sir.
Yes, sir.
So did you, I mean, get a proper idea of this remote sensing section along with this video lectures which are there?
Yes, sir.
Yes.
Okay, so I hope that this will be useful for you for your work, or like for any other thing if you are doing in this area. Okay, so now in the next lab we will see the GPS data sets. We will see the sites which will give the data, and we will see the actual GPS data as well. How will it look like through satellite? Okay, so meanwhile, thank you for joining, and goodbye. Good night.
Good night, sir.